So first of all, thank you so much for being here and for participating in this live discussion on how water quality modeling can be done and how water quality models can facilitate utility engineers, hydraulic modelers, and the utilities in general, contractors, to ensure a very good high quality of water to its consumers. Before we begin, let me introduce myself. My name is Tanay Kulkarni. I am a consulting engineer working with DTK Hydronet Solutions. I am also one of its co-founders. I previously worked, as Ashish mentioned, we both worked with Bentley Systems. I was a technical consultant with Bentley Systems, responsible for water, wastewater solutions in Asia, Pacific, Middle East, some regions. You can also follow me on LinkedIn. I have a YouTube channel. If you want or are interested in learning more about how hydraulic modeling can be done, I would encourage you to please go and check out that channel. So let's talk about the agenda and let's jump into the core of today's webinar. The agenda today, we are going to look at the introduction to water quality modeling. And then I'm going to take you through a live example where we are going to perform water quality modeling on a particular network. So that's going to be an agenda for today's session. What I've observed, I have deliberately kept this image on the screen. Most of the times we know what data is, we have sensors, we capture data in some form or the other. Using that, we generate some information. But the main issue or the challenge that I have observed in past 10 years of my career, of whatever limited experience I have, is we are incapable of bringing an impact, taking decisions based on the models that we created, right? We simply use models for only one purpose, that is to design the diameter of the pipe, isn't it? That's what I have observed, and it pains me a lot because the hydraulic models are not just limited to planning process or designing stage. It is much more useful when it comes to systems operations, systems performance optimization, and systems maintenance. So today we are going to look at one such application of hydraulic models in the area of water quality modeling. But let's look at why water quality modeling is required. See, we ensure that water is treated, right? We induce chlorine into the treated water, and we check water samples at the consumer end, and that gives us fair idea that okay, water quality is, the water quality KPI is checked. However, it's not that simple. It's not that simple. For example, we might not be looking at the areas where we should be looking at, right? We should, for example, this water that we treat and we transport to our consumers undergoes through a spatial and temporal variation, right? It goes through bends and joints and leaks and whatnot. It crosses everything and then it reaches our consumer end. So there is a huge spatial and temporal variation in quality of water inside the network. And it's not as simple as what is the pressure at junction A and what is the pressure at junction B. No, even at the junctions, there are many transformations that are happening when it comes to water quality. It is essentially complex because hydraulic mixing patterns are involved and water quality transformation. This water is reactive in nature, right? The chlorine, the treatment, the disinfectants that we have added to our water are reactive in nature. That means the quality changes over a period of time, isn't it? So it becomes a bit more cliche, I would say, to accurately and to very precisely model what is happening through the network, that too with mathematical background. As you can see over here, it follows myriad pathways from treatment up to the consumer tap. Water quality at consumer tap will vary significantly over time. So when we say over time, we just not mean that over seasons it would change, or over months it would change, but even if over minutes. So if you're sampling water in the morning, the quality might be very different, very different as compared to a sample that was collected in afternoon hours, right? So it is very, very dynamic. It is very, very volatile, not in terms of reactions, but in terms of the quality. The quality change keeps on changing dynamically. And even at different, you would observe different quality in different taps. So if you have a neighbor, that neighbor might complain somewhat, have some issues related to water quality. However, just, you are just the, wall to wall connection, and you might not have or face any water quality problems. So it is very difficult, very complex when it comes to mathematically understanding and uh, fixing how the water quality in the network is changing. These travel pathways and transformations are, as I told you, are very difficult and complex, if not impossible, for any experienced engineer to determine or to gauge or to understand. It involves travel times, it involves blending of the constituents, water quality throughout the system, how the water quality is blending throughout the system, and mathematical models of hydraulics and water quality. So these are two different, they analyze the system differently. There are two different approaches of analysis of flow through water networks and analysis of water quality inside the network. So these are two very different things. Using these models, using these mathematical models, uh, we can uh, generate a method of estimating movement of water and its transformations, quality transformations, and we can understand or estimate how water quality is at any given point in time. So we need water. See, as you can see in this image, you have an image inside of a tank, right? Can you all see this pathogenic microorganisms that have been found at the base of the tank, right? So it is very, very crucial. And what are the uses of water quality modeling? First of all, we can understand if there are multiple sources that are available or that are present in our network, we can trace that which source is, how water from individual sources dispersing in the network. Secondly, we can understand how the water is aging, right? As I told you, includes disinfectants, for example, chlorine, and this chlorine ages over the period of time. It decays over the period of time, right? So higher the age of water in the system is, poorer would be the quality of water. So we can understand that. And then using water quality modeling, we can understand the concentration of non-reactive tracer compounds. For example, if you have some tracers, right, you may have some sodium form of, you may have fluoride that you are tracing through the network. You can do that. You can understand what is the concentration of individual tracer at individual points in the network. Along with that, we can also understand how this constituent, for example, chlorine, is decaying over the period of time, right? So we can understand what would be the residual chlorine concentration at any given point in the network, at any given point in time. So that is very interesting to understand, because the water that is treated on day 0 might actually reach the consumer on day 7 or day 8, and you never know, right? You might be under an influence or under an assumption that water is being treated and that's all my responsibility. But we also need to understand when was the water generated, treated, and then how much time does it take for the consumer, it to reach the consumer, right? And when it reaches the consumer, what would be its quality? And we want to ensure that quality, right? We want to ensure a better quality when it reaches the consumer. And we can also understand the growth of disinfectant byproducts. These are also called as DBP. See, this chlorine that we induce in the network, as it disinfects the water, it has a residue, right? And this byproduct, right? And it is. Can you all see this image? It is in the form of biofilms. If you don't know what biofilms are, you can simply Google it and you can understand how disgusting that might look, right? This is a clear water supply pipeline, drinking water supply pipeline, and this is the development of biofilm on the interior of that pipeline. So this is, see, this is disgusting. Pardon me. And now we know that, looking at the uses, now let's see how do we apply it to our engineering problems, to solve our engineering problems. First of all, when we are planning a system, right, you can fix the location or size of the tanks, and you can modify the system operations to reduce water age. So if the tanks are, are of very high capacities, there would be slow, the tanks would be cycling very slowly, isn't it? The tanks would be filling slow, it would be draining very slowly, and this would increase the age of water inside the pipeline, inside the tank. And as the age increases, the chlorine decays. So that is one of the application. The second application might be the degree of intermixing of multiple sources. So if I have multiple sources that are supplying water into the system, I need to also understand how water from individual sources mixing in the network, so that if I have some problem at one particular source, if I have some problems such as high salinity or traces of fluoride or arsenic at one particular source, or if one particular source is compromised, then how the water from that compromised source will travel through the network. This is very important. And then we can also understand what would be the effective sampling locations in the network. Where should I be looking at? This is very difficult. See, if you are working on some real life, very big, huge mega water supply systems, the distribution networks are very complicated. These are having interconnections, unmapped pipes, and there are so many other challenges, right? So looking, where should we be looking at? Where should we be collecting the water samples from? This again becomes an important parameter, right? So using water quality modeling, we can understand what should be our effective sampling locations. So we can also understand best location or dosage, the amount of dosage for rechlorination stations. If we need a rechlorination station, and if so, what should be the dosage, right? How many milligrams per liter should be the dosage? What kind of rechlorinator should it be? Right, that kind of decisions can be taken very efficiently using hydraulic models. Yes, you can understand vulnerability to external contamination. If there is some leakage in the network, you can, if there is some external contamination, for example, we all know during low demand hours, the pressure in the system raise, right? They are high, pretty high. And during off demand hours, the external water might enter the system, especially during intermittent supplies. So we can understand if this is one particular location is a contributor, and then we can understand how that contamination, how far that contamination will spread over the period of time. This is very realistic application of water quality modeling. Since we are working on mathematical models, we can strategize things beforehand. This is very important. And by far, this is the most important application of hydraulic modeling in general. We can decide before we actually implement something. If I want to optimize my operations, I can optimize the operations on the hydraulic models first before optimizing the operations or before changing my operational strategy, so that we can understand how the system is behaving over under those operational conditions. Now let's look at the governing principles of network analysis. We all know that when we talk about water supply network analysis, we apply principle of conservation of mass, we apply principle of conservation of energy. If you are working on some transient analysis, we apply principle of conservation of momentum. So these are all the network analysis principles that we apply. However, when we talk how different is water quality modeling as compared to hydraulic modeling, when we apply water quality or when we want to generate water quality models, we have different sets of principles that apply. So first one is advective transport of mass within the pipes. This equation essentially says that water, the constituent which is induced in the water that is flowing through the pipe, uh, will follow the same velocity and will uh, follow the same route as that of the water that is, or the fluid that is flowing through that pipe. The second one is mixing of mass at pipe junctions. So far, we just know junction is a point in the pipeline, right? But in practice, can you all see this? Is that junction offering complete mixing at a junction, right? Complete mixing of water quality at that junction. So junctions are not just points, right? These are spaces. So how water quality transforms over that space or that region is also important. So we apply this particular equation. I'm not going to go through this equation in detail, but just to give you an understanding. And then we have containers in our network, right? What are storage containers? Tanks are our storage containers. So there would be a large quantity of water or mass of water that will be entering the tank, that will be leaving the tank, and there will be some rate of change of mass within the tank, right? So we also can understand how the water quality changes as all of these things are happening at storage places or at tanks. So we can also understand how mixing of mass can or happens inside the tanks. And for that, I believe few of you might have heard these terms: complete mixing, FIFO, first in, first out, last in, first out. This last in, first out is very common in places where you have tanks, floating reservoirs, floating tanks, which have only one pipe, right? The water that enters the pipe is the same water that comes out of the of the tank, right? Or then you might have compartmental tanks. We are going to look at these. So first of all, let us look at the techniques that we apply or we can apply to model or to perform water quality studies. First of all is age. We can understand what is the age of water inside the network. Now, age is nothing but time spent by water parcel. Water parcel is nothing but a primitive particle of water that enters the system, right? And new water, we all know this source that we have, WTPs or pumping stations, the sumps. These allow new treated water enters the system from these sources, and old water is consumed by the consumer, right? So essentially, in terms of core modeling, we can say that this is a reactive constituent whose growth rate follows zero order kinetics. Now, what zero order is? Zero order, essentially, this indicates that after every passing second, water will be one or that particular quantity of time older. So after every second, water becomes 1 second older. So this is what zero order kinetics mean. The second is you can model source or contaminant traces, or you can perform this tracing analysis on the network. So you can understand what percent of water is coming from what particular from a particular source, which is reaching at a particular node in what time. So this is very important, right? And we can also understand if there are spatial patterns, right, which are temporal, in nature, how water is blending over the period of time from one source to another, inside the network. This is what we are going to perform later today in this webinar. And the third, one of the most important, is constituent growth or constituent decay. Now, when we say constituent growth, I mean how the disinfectant byproducts are growing in the system. Or when I say constituent decay, I mean to understand how the chlorine, residual chlorine, is decaying in the system, or the chlorine is decaying in the system, right? So this is also one of the very important applications or techniques that we apply for water quality modeling. Now, for water quality modeling, we are going to look at this particular software, which is WaterGEMS Connect Edition. WaterGEMS is essentially a hydraulic modeling software. So it is it gives you hydraulic models, which are a mathematical replica of your network. And we are going to perform the next exercise on this particular software. So let us first look at what constituents are. First of all, when I said constituent tracing and constituent decay, see what can be the constituents. Salinity can be one of your constituent, right? If or hardness, right? Fluoride, if you have, you can model constituents such as chlorine or chloramines, which are disinfectant constituents, or you can have DBPs, right? So these are all different constituents that you can, interestingly, you can also model taste and odor inside this these hydraulic models. And I'll just quickly tell you this, because if I don't tell you this, you will not understand what exactly we are doing in the software. Always remember, software is a tool. I have always said this, and I'll again reiterate this in this particular webinar. It doesn't have its own intelligence. You are the one who is operating that software, so you are the one who should be able to, or who should understand what's happening behind the graphical user interface, right? Software offers a great user interface, and it facilitates heavy operations very quickly. That is its application, right? But we need to understand. So let's take a look at what's first order degree, degree or first order decay. What does it mean? It essentially means that your concentration is going to decay. It's going to decay or reduce over the period of time. But as you can see on this particular graph, it is not a linear relationship, right? It is a non-linear relationship. So we can, this is what we mean. For example, if we induce chlorine in the system, it is not going to reduce in a straight line, right? It is going to gradually reduce in the system, right? So this is first, it is very frequently we use this for understanding what is the residual chlorine in the system. Okay. And then what is zero order growth or decay? Zero order growth or decay means linear. When we say linear, age is an example, right? I have mentioned in the slide, age is an example. As the time spent by the water parcel in the system increases, the age of the parcel increases, or the concentration increases, right? So this is zero order growth or decay. And the third one is first order growth to equilibrium. So these disinfectant byproducts that I just showed you, right? Biofilms or TBH, these trihalomethanes, these would come to a point of saturation beyond which there will be no growth. Okay, so we can, for understanding or for modeling these DBPs, disinfectant byproducts, we generally apply first order growth to equilibrium while modeling the quality of water inside the network. Now let me come to the, let me tell you or explain you what our objective is, and what are the problems that are lying in front of us. And we are going to solve these problems by performing live study onto our model, our hydraulic model. So here we have a network which has got two sources, reservoir 1 and reservoir 3, and two storage units, tank 1 and tank 2. Both the tanks, tank 1 and tank 2, are tanks that are floating on the system. So what happens is, can you all see this pump 4 on this screen? Now, as the water level in this tank goes below a certain level, then this pump starts. And as it goes above or beyond a certain elevation, this pump drips. Okay. So this we have in our model, we have an initially calibrated hydraulic model, which has extended period simulation scenario inside it. And what we are going to do, first of all, let's look at what we are going to learn. We are going to learn to set up network scenario to investigate how the blending of two sources happens or takes place into this network. Which two sources? R1 and R2. We are also going to look at residual analysis or chlorine analysis with wall decay. So we are also going to look at how much residual chlorine will we be getting after we consider wall decay. So there would be a boundary state condition uh, where this chlorinated water will be reacting to this interior of the pipeline. And I also want to account for that, right? So that we are going to look at, and then we are going to perform a water age analysis, how water is aging in the system. So we will consider tank mixing models and importance of setting good initial concentrations at the tank. Essentially, before you start performing water quality analysis, it is important that you know what modeling basics are, and you have a well calibrated, a decent calibrated hydraulic model. And you need to understand what the system planning department had forevision or envisioned, and how the operations in the systems are. And you need to have a functioning extended period simulation hydraulic model before you start water quality modeling. Now, the first problem. What is our first problem? To understand, or we are going to model total dissolved solids, TDS. We are working on a system with two sources. One source is R1 and one source is R2. R1 has a low total dissolved solids concentration. At R1, we have 250 milligrams per liter. At R2, we have 600 milligrams per liter. And this constituent might be anything, right? It might be salinity, as I have already explained you. So we have two sources, and I need to understand how this TDS is modeled, or how the network performs. The low TDS source runs continuously. This R1 is running continuously. There is no control, right? It is a reservoir that is continuously feeding this system. While TDS source, high TDS source comes only on when the level in the tank drops below 50 meters. It goes off. That means the pump trips off. It turns off as soon as the level increases up to 51.5 meters at tank T1. We want to investigate the blending of these two sources in the distribution system. I believe everyone understood what our objective in this particular problem is. Now let me, instead of explaining you all the three problems, let us look at one problem, and then we'll go into the hydraulic model. So let us open this hydraulic model. Can you all see the hydraulic model? Can you all use the chat box and let me know? Good. Thank you so much. And we have this hydraulic model. Let us go to the calculation options first of all. First of all, see, can you see this calculation type? This is constituent. So far, for those of you who haven't worked on water quality modeling before, in that case, the default is hydraulics only. The calculation type is hydraulics only. However, we are now going to model water quality studies on this hydraulic model. So we are going to create a new, let me just duplicate it, and I'll say that this is constituent. I'll just rename it. And in this particular calculation option, we are going to set the calculation type to constituent. Can you all see that? Constituent. Now, this is essentially an extended period simulation. So let us first do one thing. Let us analyze this system as we have. Okay, before performing anything, let us compute the system. And it is giving us a calculation summary of 72 hours of the day. 72 hours, that means how many days? 3 days. And now let us look at these two tank elevations. Let us plot a graph of how water level in the tank is fluctuating over the period of these 72 hours. So can you all see how the tank water level is fluctuating over the period of time? Oh, sorry, this is not water level. This is flow through the tank. Let me show you the level calculated. Can you all see how water enters the tank, how water drains the tank, drains from the tank? These are two different tanks. T1 is red color graph and T2 is blue color graph. So this is how the water level is fluctuating. Let us also look at the patterns that are set. so that we understand. So as you can see, there are two patterns. One is a residential pattern, hydraulic demand pattern that is subjecting to our demands, and the other one is a commercial pattern. So there are two demand patterns that are applied to our hydraulic model, hydraulic demands, and we simply computed this network over a period of 3 days. Now, let me also show you the controls that are set on this model. So let us go to components, controls, and I wanted to show you this because I wanted to show you this particular control. Can you see? As soon as the tank hydraulic grade increases or goes beyond 51.2, then the pump 4 status is off. And if the tank hydraulic grade is less than 49.7, that is as good as 50, then the pump status turns on. And what is this pump name? Pump 4. So let me close this control and let us zoom into this pump 4. So can you see this control, this segment that is associated to this particular pump, right? So it is indicating that this particular pump is controlled with what? With the tank level or tank hydraulic grade at tank T1. All right, so this is what we have. And now let's see how the pressures are fluctuating at different junctions. So junction J10, J13 and J1. Let us plot a graph. So these are kilopascals, fair pressures, right? And as you may see, as soon as the tank is supplying water, these pressures are dropping. And as soon as the tank or the pump starts, this pressure increases. So you may observe or the behavior of your existing extended period hydraulic model. Now, let us jump into water quality modeling. As we saw, we are going to consider a 250 milligrams per liter TDS at reservoir 1 and around 600 milligrams per liter at reservoir 3. And we are going to consider that the initial concentration at these two tanks are 300 milligrams per liter, right? You'll have to check with have a sample at the tank, and then you can come and enter that value. So for initial run, we are going to go ahead with an assumption that the tanks are having 300 milligrams per liters. Now let us go to alternatives, as we are going to create a scenario to check what will happen if we consider this particular given condition. Now let's go to alternatives. Let us create a constituent alternative as we are working in water quality. Let me rename it to TDS of 300 initial at the tank. And let us double click and open this alternative. You previously have a constituent, but we want to create our own constituent. So let me simply click this ellipsis. And here we are going to create our own constituent, TDS of 300 at the tank. And what we are going to do is the rate of bulk reaction rate inside the water and the reaction rate at the wall of the pipeline with the reaction with the pipe. We are going to consider it as 0. Why? Because this is a conservative source, right? The quality is not going to change. We are just wanting to understand how the constituent is flowing in the network, right? We are just tracing its flows. So we are going to keep the rate as it is. Let's close this, and we are going to use this TDS 300 over here. However, we are also going to set an initial concentration at the tank of how much of around 250 or 300 milligrams. Can you all see this initial concentration at the tank? So initial means before the run. Okay, so we have 300 milligrams per liter, and the reservoirs. Can you see this reservoir table? The initial concentration of water of this TDS at the reservoir 1 is 250, and at reservoir 2 it's 600 as per the given statement. Okay, and now let us close this. This is how we create an alternative. We have created an alternative. Let us create a scenario. Where are scenarios here? Let me right click, create a new child scenario. Let us call it as TDS 300 initial at tanks. Okay. And inside this particular scenario, which alternative should we be changing? We should be changing the constituent from default to TDS, the newly created 300, TDS 300. And we have also created this constituent calculation option, isn't it? And let us set this duration to 288 hours. That is 12 days. So we are going to simulate a 12-day analysis on, perform a 12-day simulation of the network using friction method as Hazen-Williams, calculation type as constituent, and the time as duration as 288 hours. Let us go into this scenario and let us change this steady state to constituent. Let us make this scenario as our current scenario. Let me close calculation options and alternatives. Let us compute. So after computing this, it is going to analyze the constituent. So it has computed. Let me show you the summary for all 288 hours. For all 288 hours, it has given us a mass balance in the system. Now let me color code this pipe on the basis of concentration calculated, because we are interested in how the water is dispersed or how these two sources are mixing. Water from these two sources is mixing. So let us create a full range. And this particular reservoir 1 has an initial concentration of 250. So let us say this. If it is less than 250, then I'll understand that the color should be green. And if it is more than 250, that means water is from reservoir 3. If it is more than 250, then I want different colors. Did you all understand? So as long as water is coming from reservoir 1, it would show us 250. That is green color pipes. And as soon as water starts coming from reservoir 3, which is high TDS source, 600 milligrams per liter, it will have different colors. So let us click apply and OK. And let me rename this as TDS, concentration TDS. Let us copy this concentration color code and let us also apply it over junctions so that the junctions will also be color coded. So this is what we have. Can you see this time browser? Let us open this time browser and now let us start modeling. Now pay attention what is happening. At 1 o'clock or 1 hour time step, this reservoir is pumping water. Can you all see this pump on condition? So this reservoir is pumping water and can you all see this how water, so all non-green color pipelines are the pipes where the concentration is high. The TDS is higher than 250 milligrams per liter. And can you all see this? It was this water that was coming from this reservoir R3 is already stored in this tank 2. And that water is coming from that tank. The water that was collected from reservoir 3. And let us now see or increase the time step. This is going to be really interesting. Can you all see how water has now, it has now moved towards this because it's filling the tank? Can you all see this? P15 is now filling the tank, right? So can you all see how water, let me annotate, which is coming from, let me change its color, which is coming from this source is now dispersing in the network. And this source is, by the way, is already supplying water. This is an uncontrolled source. So it will be supplying water for all 24 or 7 to 12, all 12 days. However, can you see this water? Now it will try and, it will fill the reservoir and fill this tank. Right now, let us go to the next step. See, it started filling both of the tanks. And can you all see the water quality in the entire network and how much water is coming from, or which are the locations where we have lesser or lower concentration, lower TDS, right? Can you all see? And as soon as, let me also right click and create a graph of this particular tank. And let us create a graph for percent full. So pay attention. As soon as, let me drop it over here and then explain. Pay attention. As soon as this tank is filled, as soon as that point is achieved where the tank is filled, can you all observe this pump has tripped? It is off now, right? There is no water coming from this particular source, right? And now can you all observe the rest of the network? Can you see now the water that was filled in the tank is now coming out of the tank? See? And how people are consuming this high TDS water? Pay attention. Now the entire system will start becoming greener. Why greener? Because it is now being supplied from R1. See? Can you all see that? How till what time, till what point in time? Until the tank empties and this pump starts. So pay attention what happens. As soon as this pump starts, after 15 hours, as soon as this pump starts, see the flow direction has reversed, right? Now consumers are getting water from different source which has a higher TDS. Can you see the another overlapping impact and then overlapping impact? So we are going to understand how this cumulative impact happens over a period of 12 days, right? I think I am explaining, you all are getting this. Can you all see the pump is off? Yes? Good. Now let me, instead of going one time step at a time, let us go play and animate this over a period of time. See, the tank is full. Now the tank is supplying water. The pump is off. And how? Did you all understand what is happening in the system? And again, this high concentration or TDS water is now pumped into the system. Now, let me pause it over here because this animation just is not important. Just the animation is not important. Let us select these two tanks and let us create a graph of these two tanks. Instead of flow, let us now see, correct. The mixing and consumption and the blending is important, isn't it? Now let us see, look at the results, concentration calculated at individual. Can you all observe this thing? Initially, the concentration was 300. We assumed that the concentration is 300. Can you all see what is happening over a period of time? How the concentration of this high concentration water is filling the tank. Which tank? T2. Can you all see? It is cumulative accumulation of. Can you all observe that? Can you all observe that? It is cumulatively accumulating. Let me annotate so that I can help you understand this. Can you see this constant or a gradual increase of concentration at a particular storage? Right? And can you all see it is very flat when it comes to tank T1? It is relatively flatter, isn't it? So this is important. This will give me an insight of what is happening in the system if we consider that. And then we can see if that is, if ever we achieve any equilibrium condition at these tanks. And you would use these models to calibrate the initial. So if this is happening, what we would do, you would go back to your tank, which tank? T2, and you would cross check or you would recapture, resample the quality of water at tank T2, because this is, can you see? This is constantly increasing. However, can you see an equilibrium state being achieved over a period of 20 or sorry, how many hours? Or over a period of 12 days. Can you all see this particular part of around initial? What was our initial concentration? 300. So it is being achieved. Can you see that the tank at which tank T1 is a calibrated tank. However, T2 is not yet settled. It is still, so you want to now check, or you want to go back to the tank and check if the value that you have entered, this initial concentration of 300, is it logical or not? Is it correct or not? Right? So this is how you understand water quality models. Of course, you can also select particular junctions. Let us say these three junctions, and you can compare. Let me plot a graph. We can compare the concentration from different sources at these three junctions. So let us open water quality results, concentration. Let me increase it. Can you see what is happening? J1, this junction J1 is red, blue color on the graph. The red one is J13 and the green one is J16. See what is happening. J1, which is near to the source R1, can you see a constant concentration? Let me uncheck the rest of the two junctions. Let us simply observe this concentration at J1. Can you see? Initial concentration was of course 0, but as soon as water starts entering from reservoir 1, can you see a constant concentration of 250 milligrams per liter? Right? So that means at J1, we are not, the consumers would never get water from R3, would never get water from R3. Did you understand what's happening? So you would never hear complaints of water quality from which region? Region near J1. Did you all understand? And now let us compare this with the rest of the two junctions that we have selected. And when you compare that, can you see? For few hours, there would be no complaints. But as soon as water from reservoir 3 starts entering the system, can you see higher levels of TDS, total dissolved solids, at the consumer? Can you all see this? More than 250. And during these hours of the day, you would get complaints, or your quality at that duration for that particular locations would be compromised. Did you all understand the first part of this exercise? How TDS modeling is done. Now again, remember, we have not, this is it is a conservative, the quality would not change. Quality in terms of chemical properties would not change, isn't it? Right? It is simply the constituent. So this is zero order. There is no reactive measures that are taken, right, happening in the system. Now let us go back to our system and presentation. And this is what we have done. We wanted to investigate how this blending from two sources is happening throughout the network. Did you all understand? Now let us perform the next exercise, which is understanding the residual chlorine in the network. Did you all understand the first exercise? Now let's look at this. Now in this exercise, we are going to look at this diffusion coefficient. I'm going to explain what it is. Diffusion coefficient is a function of fluid, the size of diffusing particle, that is the chlorine gas or constituent. And so larger the molecules diffuse more slowly, or slower would be the diffusion. Temperature of water, obstruction by pore structure or sediments or any other material, even the bends, and the rate of mixing of water. Now we are going to perform chlorine, residual chlorine. But before we do that, I'll just quickly tell you, the potential problems that might happen when we consider chlorination, when we perform chlorination or residual chlorine water quality models. First of all, the tanks. The tanks are storage containers, so they would, increase the age of water. They would contain water. There are different types of tanks, as you can all see over here, right? And you can model all these tanks inside the hydraulic model to understand the behavior of the chlorine decay. Can you also this completely mixed tank, FIFO, first in, first out? This is what generally happens in tanks which are floating on the system. Then you may have last in, first out, and then you may have two compartment system, right? So these are tank mixing models that can be done inside the software. Why we want to, I wanted to show you this because depending on what kind of mixing model you apply at the tank, your quality would drastically change. As you can see, can you see this graph on the screen? See? So this red color is complete mixing. The cyan color is two compartment tank. The same tank operating with different mixing models, and the blue color is last in, first out, and the green color is first in, first out. So wanted to show you that even such modeling should be done before you finalize a particular tank in the network when it comes to water quality analysis or ensuring good proper water quality in the system. Now let us go and perform the chlorination analysis. So now what we are going to do is we have created one scenario for TDS. Now let's go to alternatives. We are going to create another constituent. Let us say this is our chlorine plus wall decay, because you also wanted to understand what would be the wall decay. And let us enter that. See, previously we had created this TDS 300 constituent. Let us now again create a new constituent. New. Let me rename it as chlorine plus wall decay. And over here, pay attention. We are now going to consider not just the decay of chlorine inside the fluid, but also its relationship with the water or the pipe surface, the biofilms that are already present. So we are going to enter bulk reaction rate and zero order wall reaction rate. As I told you, now the concentration is going to reduce, right? So we are going to use, instead of zero order, we are going to use first order, right? First order decay condition. And the bulk reaction rate that we are going to enter is minus 0.3. And this is the diffusivity that I explained in the slide, right? This is how many area square meters covered per second, right? Now, let us enter this first order, the relationship coefficient of reaction coefficient between the water and the pipe surface. This is negative again because it is going to decay. 0.305 milligrams meters per day along the line, because this in this particular case the length would be, remember the advective principle, this is going to apply here. We'll take the questions later after the session. Now we have created a constituent. Let us consider that particular constituent in this particular alternative, the new alternative that we have created. And we are going to consider these reservoirs that are pumping water into the system. These are pumping treated water. So the chlorine that will be that will be present in the treated water will be 1 milligram per liters. So that we are going to set over here. So let us go to reservoir tab, and the initial concentration I am setting it to 1 milligram per liter. Okay. Now let's close this. Let us go to scenarios and let us create a new scenario. Chlorine plus wall decay. We are considering both. And let us set this to constituent. And let us set our constituent to chlorine plus wall decay. These two alternatives will make this scenario as our current scenario. I'll close alternatives and let us compute. Again, it has given us a calculation summary. Let us close that calculation summary and see, presently the pipes are green because it is considering the concentration calculated with TDS study, right? Previous scenario. Now I'll just uncheck this and I'll create a new color code for our chlorine concentration. So I'll go to concentration calculated, because this will range between 0 to 1. So can you see 0 to 1? And then point to after every, in 5 equal steps. However, smaller the concentration is, I want to prominent must should be the pipes, right? So I'll just invert this color code, because as the concentration is decaying, reducing, I want to understand that these are the locations where we should be prominently looking at. So I'll simply reverse this color code, and then let us apply and OK. And I'll copy this and rename. First of all, let us rename this as chlorine residue or residual chlorine. And we will copy this. Oh, sorry. We will copy this and paste it at junctions as well. So this is how we have. And let us go to this particular thing. Initial chlorine at all the junctions is 0. Okay, so now the first time step, water will be starting, chlorinated water is entering the system. Okay, that is what is happening. So let us see what is happening at time step 1. As soon as the time step 1, we enter this time step 1, can you all see water that is gushing into the network from reservoir 1 and reservoir 3, because reservoir 3 pump is on, right? Can you all see? And can you all see this or less concentrated chlorine water that was present in the tank, that is coming out of the tank, that is entering the tank, isn't it? First of all, also let me, before I explain you the other things, let me also show you in tanks. Can you all see this tank mixing models? You can set it as you want, as per your condition. Okay, is it last in first out? Is it first in first out? Is it completely mixed? So you can fix that model over here. Okay, inside alternatives. And now let's go to the next time step. Can you see the water quality improving in the system? And see, water quality is improving and improving and improving and improving. Let me also right click and create a graph. Level calculated, because I want to show that it will keep on improving until a point where the tank is full. Now see what happens. In the next time step, the pumps have stopped. The pump has stopped, and now whichever water was stored in the tank is now coming and returning into the system, right? Now see what happens. Can you see the water quality degrading, right? Can you see the older water now re-entering the system? Initially, as both the pumps were on, all this new water entered the system and all the old water was filled in the tank. Now that stored old water is now re-entering the system. Can you all see that? Can you all imagine what is happening using hydraulic models? And it will keep on happening until what point in time? Until the tank is completely drained, this particular tank. And then see, and in the next point time step, see the pumps have all started again, and this water, now let me show you it over the period of 12 days. And now see, this is what is happening. You can understand it from here, but we can also select these two tanks and let us plot the concentration at these two tanks. So let us plot a graph of chlorine concentration inside these two tanks. So let us go to water quality, concentration calculated, and let us click OK. Can you see how chlorinated water is cumulatively stored and how the water quality is gradually maintained in the tank after every cycling, every cycle? Can you all see that after every cycle, new water is entering the system? Old non-chlorinated water is coming out of the system. Can you all see that? And just a moment. Yes, our objective is to ensure as high or as good of a quality of water at the tank, so that as the this is still 0.4, it has not yet reached 0.4 milligram per liter, right? whereas the new water that is coming into the system has a concentration of 1 milligram per liter, right? So our objective is to ensure such an operation so that better quality of water is stored in the tank. Now, can you all see again an equilibrium state has, we have obtained an equilibrium state at both the tanks. Now, can you tell me, just by looking at this graph, what would be the average quality or concentration of chlorine that you should expect at tank T1 and tank T2? Yeah. So at tank T1, it should be around 0.2, in the range of 0.2, isn't it? Yes or no? Use the chat box and let me know. Yes. And at tank T1, I think, yes, T1, can you all see this average quality of water? Right. So this is just at the tank, but you can also see, yes, sorry, right, Moinuddin, and see what is happening in the rest of the network. Again, you can do understanding, you can understand what is happening or how these consumers are getting chlorinated water, what would be the concentration of chlorine over the period of 12 days at different consumers. So these particular consumers at J1, J16 and J13 are getting better quality of water. Can you say that by confidence? With confidence? Can you say that with confidence? Can you see what is the average? Can you see what is the average residual chlorine at these consumers? Yes. So this is how you perform a residual chlorine analysis, considering a wall decay, right? And now, lastly, we are going to look at the third problem statement. We started late, so we will continue for a few more minutes. I believe all of you are okay with that. I hope. So this is our problem statement. The last one, age analysis. Water enters our system, right? And old water is consumed by the consumers. So we are interested in understanding what is the age. What do you mean by old water? What is the exact age of water in the system? So now let us perform this age analysis onto our network. Let us go to alternatives again. We are going to create a new age alternative. Can you all see this age alternative? We are going to create a new age alternative, new child alternative. Let me rename it as age over a period of 288 hours. Let us enter that alternative. And here essentially what we want to do is we want to specify some initial conditions to our network. So we want to assume that what is the existing age at the start of time. So at the beginning of our simulation, we are assuming that all the water in the system is 1 hour old. That is my just initial assumption. Okay. So I'm assuming that this initial age at all the junctions is 1 hour. Water at all these junctions is 1 hour old. And typically globally, I mean, with all this research papers, and it has been observed that at the tanks, typically the age of water is around 72 hours. 65, 62, 72 hours, in that range. Okay. So let us assume the worst condition, that at the tank, the age of water is 3 days, 72 hours. So let us go to tank. The initial age I'll specify. I'm assuming, I don't know, but I'm assuming, and then we'll rectify. We can rectify what should be the age. Okay. But typically it is 72 hours as per the papers that I have read. Okay. And at the reservoir, at the treatment plant, it is newborn, new water, right? So the age would be 0. So at the reservoir, we'll assume an initial age of water as 0. Let us create a new scenario now. See how handy scenarios and alternatives are. We'll create a new child scenario. We'll do this as age analysis. And here we'll set this to I'll have to create an age. I'll create an, just a moment. I'll have to create a calculation option. Let me rename now change. We are not tracing constituents now. We are doing age analysis. However, in the latest version of WaterGEMS, you also have this one calculation type that will take care of all the things. So let us go to age. Time is 288 hours. Hazen-Williams formula for calculation head loss, but that is hydraulics. Okay. And we are going to set this calculation option to our newly created scenario. So let us go and perform age analysis. Again, this would not be default age. This will be which alternative? Age 288, the newly created alternative that we have over here. Now let us make this scenario as our current scenario. Close this, and let us color code the pipes and the junctions based on age now. Sorry, age calculated. Oh, there is no, so we'll have to perform compute the network. Let us compute the network for 288 hours, that is 12 days. It should give us a calculation summary. For all 288 hours. Let us close this. Let us now create color coding for pipes and junctions based on age calculated. Now pay attention. Can you all observe what is the maximum age that has been calculated? 138 hours. Can anyone please divide it by 24 so as to get the number of days? And please type it in the chat box. So smaller the age is, greener would be the pipe, and red color indicates larger age. Okay. Now let's click apply and OK. And now let's copy this and paste it over here. And let's simulate this. Good, 5.77. So at approximately 6 days old, right? So the maximum age of water in the network is already, we know, right? Just by looking at the color code, right? So it's 6 days old, right? So now let's look at what is happening to the age of water. Again, let us, instead of just animating the system, let us look at graphs, because graphs give a better understanding of what is happening to our system. Water quality, age calculated, and okay. Can you all see this now? Okay. Let me put it over here and let us go through or browse through the time. See, new water. 5 hours, new water. Let me just play it. See the age. Can you all let me pause this over here and let us have a legend over here so that we'll understand what color indicates what property. Can you all see this legend? And now let us click play and see observe what is happening. See, it will never be like, so these tanks are floating on the system. It will never, in such cases, it will never be like new water entering, old water coming. No, it will be water that was coming from the tank is reversing back into the tank, right? Can you all observe that happening? In countries like India, we have tanks that are completely separated from the system. They are disconnected. So in that case, you have a separate inlet where this water is directly exposed to atmosphere. Okay. And then you collect water and you have a separate outlet pipe. In that case, you would not observe this. Okay. In that case, it will be first in, first out condition. Can you all see how the floating tanks are behaving? And can you see how much time is it taking? How gradually the age is. Let me pause this. Can you all see? As soon as this curve drops, it indicates that new water is entering the system. Or that is the new water that has entered the tank. Can you all observe how gradually it is increasing? And can you tell me which tank is balanced? T1 or T2? Which tank is balanced? T1, correct? T1 is balanced. Can you see it has achieved equilibrium stage much quicker as compared to T2, isn't it? So this is again important because we want to understand as soon as we supply water, which are the tanks that are going to keep on adding the age of water, right? Which are the tanks that needs to be cycled quickly? Maybe while planning a new system, you might want to work on this particular tank. Which one? T2, right? You might want to increase some demand or change some operations on T2 in order to ensure lesser age of water at T2. Did you all understand? So it is keeping on increasing. This is only 12 hours, sorry, 12 days simulation. Over a period of months and years, we want to understand what will be the equilibrium age of water at T2. Did you understand what I mean to say? This was our presumed or assumed age, 72 hours. But now you have observed that this is not balancing itself. It is keeping on adding and adding and adding and adding. What would be the hour? After how many days would it be balanced? And what would be the balanced age of water at T2? Did you understand? That is our objective. So this is how you perform water quality modeling. So first of all, there are certain prerequisites when it comes to water quality modeling. That is, I have already shown you here. Can you all see the screen? Let me. See, first of all, you'll have to have a calibrated model. Calibration is very, very important. Extremely important. The most important thing, okay, of application of hydraulic model is calibration. You have to calibrate your model. Then you have to understand how the system is operated. You have to interview the operators, and then you have to, upon that understanding, you have to create an extended period simulation model, EPS model of your network, and then you can perform this. So we have looked at problem statement 1. We have looked at how TDS modeling is done. We solved this part. We understood how this blending was happening in the system, right? How many consumers would probably be complaining about the quality of water, right? Then we performed residual chlorine analysis, where we understood how water quality, how this residual chlorine is available over a period of 12 days. And essentially this water quality, it has to be performed for longer duration, 12 days, 30 days, because it takes time for the system to balance, right? Unlike an extended period simulation where you assume that, okay, if this is your average day, it is going to cycle just like the other day. So you have to pay attention to all these things. And then we lastly saw that if there are complaints that were reported for this particular network, which is the tank that should be probably investigated, right? Which are the areas that would have older water, right? So all this, see, as water ages, odor, it comes with odor, taste fouls, right? So you have to perform such kind of analysis to the network. Now this, we would conclude our